engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast. This is the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine, with me, Chris Smith. And this week, the cells that vanish when we slim down. Are these the link between obesity and health problems like diabetes? Also, the bacteria that may be able to shield us from the forever chemicals that we're all eating. Why will 3 days over the next month be a millisecond shorter than they should be? And, as the Human Genome Project celebrates its 25th birthday, we speak to some of the key players behind this giant leap for the life sciences. First this week, what happens to our fat when we lose weight? Well, scientists in London have just made a surprising discovery. It's not just that fat shrinks, but our bodies also clear out damaged or so-called senescent fat cells at the same time. It's the presence of these cells, they think, that contribute to some of the damaging effects of weight gain, like diabetes, through producing inflammatory and other abnormal signals. The removal of these senescent cells by the body might well therefore contribute to the improved health status that accompanies weight loss, although what stimulates the disappearance of the cells in the first place when we diet, or indeed their persistence when we overeat, isn't yet known. But they might hold the key to better management of obesity and diabetes in future. Here's Will Scott from the MRC Laboratory of Medical Sciences and Imperial College London.
So we've known for a while that as fat tissue expands and gets bigger, it causes some of the normal roles of fat tissue to not function properly, and that's very intrinsically linked to the complications that people with obesity get. But we've not really understood in great depth why that happens, and even less so for weight loss. We think a lot of these processes may improve when we lose weight, but we don't really know why. And so one of our main mission statements is to understand this.
And how have you gone about looking at it?
We're very lucky to work in the clinic with patients, and so we've asked some of our patients who are obese or overweight to donate some of their fat tissue to us before they lose weight and then after they lose weight. But also we've taken healthy, lean people and asked them to do the same. This has allowed us to compare how fat tissues change when we put on weight, but also how they get better when we lose weight.
And the people that were losing weight, was that what, just going on a diet, exercise, or were they having other interventions to help them slim down?
So they've had a very specific type of weight loss, which is an operation for weight loss, which we call bariatric surgery. It's one of the most potent or strongest forms of weight loss, and that's our main reason for studying it. We wanted to see big differences so we could really unpick what was happening or the biology underneath these things.
So you get these biopsies from the fat tissue when a person is in their initially starting overweight state, and then as they lose weight you get a sample again. What do you do with those samples though? How do you interrogate them to work out what's happening?
So we're really lucky to have these amazing tools in our laboratory where we can take every single cell in a piece of tissue and all in one test, we can look at all of the cells that are there, and we can very deeply look into all of the molecules in those cells. And when we do that across thousands or even hundreds of thousands of cells, we can build an enormously rich picture of what happens in our tissues when we gain weight and when we lose weight, how cells change, how they communicate with each other, and the problems that they run into that cause these disease processes.
And what did you see when you did that on the people before and after they lose weight? How do the two compare?
One of the most important things that we see is that when people become obese, some of their cells become stressed and permanently damaged, a process we call senescence. And this senescence process increases as people get more obese. But what was really striking to us is that these damaged senescent cells seem to disappear almost completely with weight loss. So it looks like the tissue is sort of repairing itself, if you like.
Do you think those senescent cells, since their number correlates with the risk of having problems from obesity, is it your view then that they are the cause of at least some of the metabolic problems, diabetes and so on, that people who are obese are at higher risk of developing?
They're one of a number of conspiring factors. Our fat tissues become inflamed when we put on weight, and this is partly because some of the fat cells swell, they get too large, if you like, and they release stress signals, and these stress signals cause inflammation, and that process causes some of the fat cells to senesce, but also senescent cells then release different types of factors that are toxic to the tissue. So you have this sort of vicious circle of processes that all conspire together that harms these tissues.
And you note that when they lose the weight, these cells disappear. So where do you think they're going? Why are they disappearing?
So they're either being eliminated. Cells have programs where they can die, but they do that in a managed way so they don't stress the tissue out. So that's one possibility. The other is that some of the immune cells that are also there in the tissue find these senescent cells and they get rid of them. And we don't know exactly which is driving this, but what we can see is the key processes within these senescent cells that cause them to be senescent and to cause other cells to be senescent.
So if we could find a way to just go in and zap the senescent cells without the person having to lose the weight first, would that also work? If you're right, that should be the case.
That's the principle. Everything has a caveat in science, as you know. Senescence is also important in some contexts. Probably the reason that our cells senesce is for things like wound healing. We damage ourselves, the cells next to the wound senesce and they release these inflammation and kind of scarring factors, and that helps us heal. But when this is switched on all of the time, it causes us damage. So we have to always get the right balance with these types of things. There's a lot of interest in trying to treat senescence, but we've always got to be careful we do it properly and we don't do harm at the same time.
Really interesting study that. Thanks very much to Will Scott from the MRC Laboratory of Medical Sciences and Imperial College London. That work just came out in Nature. Well, sticking with what we put into our mouths, Cambridge scientists have discovered that a certain species of microbe found in the human gut might be able to help defend us against the toxic and long-lasting forever chemicals that are known as PFAS molecules. These substances, which were originally thought to be harmless and inert, are everywhere, including even in some food containers. But they're increasingly looking likely to be causing hidden health harms. Kiran Patil at the University of Cambridge MRC Toxicology Unit has found, though, that a common bowel bug actually appears to be able to soak them up.
We wanted to find out if gut bacteria in our bodies can help us get rid of forever chemicals. Their technical name is PFAS, or polyfluorinated alkyl substances. These are widely used chemicals in consumer and industrial products because they are stain resistant and they are very tough.
You find them on frying pans and things, don't they? Non-stick coatings. You go to McDonald's and you get your burger wrapped up in a nice sheet of paper that's grease-proof. That's the same family of chemicals, isn't it?
Exactly. There's the same family of chemicals. You'll also find them in waterproof clothing and shoes and so on. And unfortunately, nowadays in our bodies and in our blood.
But the ubiquity of these chemicals has arisen because of the belief that they are harmless.
These chemicals are very inert for chemical reactions. That's why they persist in the environment for hundreds of years. And initial thinking was that since they are so chemically inert, they are going to be harmless. But unfortunately, that's not the case. There have been many links shown to different diseases, including cancer, reduced fertility, reduced immunity, and so on.
Do we know how they produce those effects, these chemicals? If they are so inert, why should they be having those harmful outcomes?
Although they are chemically inert, they are not biophysically inert, right? So they tend to be accumulated inside the body, inside vital organs like liver and so on. And it can cause inflammation, it can cause oxidative damage and so on and so forth.
So what led you down the path of wondering what microbes might be able to do then?
So the gut microbes have amazing capability to deal with lots of different challenges. They're already helping us in many different ways, in terms of digesting our nutrients and so on. They have to, in their natural environment, deal with lots of chemical stresses. So we wonder whether they will also have some ways to deal with these forever chemicals.
And what did you do?
So we started our experiment in a test tube, so to say. Take a panel of gut bacteria that would represent average healthy human gut, and throw these chemicals on them and see what they do to these chemicals.
To distill that then, you'd take a population of gut bugs that you would find in the average person's intestine and just grow that in a culture and then ask, well, I'm going to add these forever chemicals and see what it does to the bacteria. Did you add them at the sort of level that if I were eating a normal diet, going about my life in general, that's the sort of level of exposure I would get?
Exactly. So we added in many different levels, like what would be exposure levels, even 10 times lower that, and hundreds of times higher that as well. So we look into what happens to this chemical outside the culture, outside the cells of bacteria. Do they disappear? And if they disappear, are they broken down or they are taken inside the cells?
And what do you see? Do they get into the bacteria?
They're not, unfortunately, broken down that by bacteria, but we see that the bacteria soak up, like sponges, these chemicals and store them inside in dense aggregates.
Really? Do all the bacteria do that? Or, because you said a mixed population representative of what's in the gut, is it certain types or species of bacteria that do it?
Yeah, indeed. So mostly Bacteroides, but not all bacteria. So, for example, gram-positive bacteria will tend not to do that.
Now, obviously, a test tube or a culture dish does not have an immune system. It's not a lining of an intestine like they would be for real. So would the same happen in a physiological environment, in a gut for real, for example? Did you test that?
No, great question. And for that, once we knew that it happens in an in vitro situation, we wanted to know whether it will happen in an animal gut environment. So we did that experiment in mice. So we colonized mice with human gut bacteria so that their microbiome looks more like a human. And then we gave them these chemicals and see what happens.
And do the bacteria do the same thing as they did in the dish? Do they soak up these forever chemicals?
Yes, exactly. That's what they did. And the way we measure is that we look into what comes out into feces, because most bacteria, they grow inside the gut, but, in a morning routine or wherever the mouse do their routine, they will come out. And we see that there's up to 3-fold increased excretion of these chemicals in mice feces.
Is your argument then that if the bacteria can do this, they are in a way protecting us from forever chemical exposure? So I eat some forever chemicals, I've got some of these microbes, at least some of the PFAS molecules will be soaked up by the bacteria, not me.
Exactly. That's what our research suggests, that our microbes, gut microbes, might already be helping us to get rid of these chemicals.
Do you know how the bugs are doing it?
So we have some molecular insights into this. We now know that there's an active molecular pumps that are taking them in, and in some bacteria actually even pumping them out.
And just closing the loop on the fact that you're feeding mice these chemicals and arguing that the bacteria appear to be interrupting the flow into the mouse. Did you measure the mouse to see if, when you do this, and they have these particular bacteria, the mouse is getting a lower dose of these chemicals?
Yeah, so we know that the mouse is getting lower dose because more is pooped out from the mouse feces. In this particular experiment, we did not measure the mice blood content simply because the way this experiment was set up and our license was that we could do this experiment for a short period. But definitely in future we have to do kind of a longitudinal experiment to see the effect on a body level.
And what about applications of this? Obviously, it's academically really interesting that this can happen and you might be able to exploit these bugs in some ways. Do you think this is a possible avenue that we could use to protect us, ourselves, from exposure to these chemicals?
Definitely. So I personally see this finding as kind of understanding how clocks and springs work, and once we understand that, we can go and venture into building a clock, right? And in order to do that, we co-founded a company called Cambiotics, whose goal is exactly this: to develop probiotics that can be taken orally, and hopefully they will help us accelerate the secretion of PFAS from our bodies.
Kiran Patil at the University of Cambridge there, and the findings that he was talking about have just come out in Nature Microbiology. So there you go. You'll have a probiotic to take for blood pressure control and another one to help you soak up the surface that you scraped off from your non-stick pan cooking your fried egg in the morning.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith. Still to come, why is the Earth spinning faster on some days this year? We will find out. But first, water is one of the most abundant molecules in the universe. Here on Earth, we see it in the liquid state, as steam, and also as a solid, ice of course. In space, though, it is so cold that it exists mainly just as ice. But it's not the ice that we know. Instead of nice regular crystals like a snowflake, space ice has got no structure. The particles exist in a random jumble, and this is called amorphous ice. But physicists have always struggled to explain why some amorphous ice is of an apparently lower density. Until now. Because with a combination of X-ray techniques and computer modelling, Michael Davis has found that amorphous ice actually contains lots of little crystals. It's a bit like those chocolate bars that have bits of honeycomb scattered through them. One of the reasons that this matters is because it makes the claim that life-giving molecules like simple proteins came to Earth from outer space a bit less likely. And that's because the structure of space ice that Michael envisages wouldn't have much room left between the molecules to pack in a cargo of chemical hitchhikers.
If we think about the atomic structure of something, it's how atoms arrange themselves in three-dimensional space. And if you think of steam from your kettle and water in your glass, it's completely disordered is what it would look like at the atomic level. The atoms just move around with no pattern that you could recognize. Whereas an ice cube is a solid and it has a hexagonal structure. If you think of a snowflake, it has a hexagonal symmetry. Whereas amorphous ice, it's kind of like we have a solid, a bit like everyday ice you put into your drink. But the atomic structure is completely disordered like the liquid. So like a frozen snapshot of the liquid.
And why should the condition be different on Earth compared to across the universe? How do you know that most of the water out there is in that amorphous form?
The conditions in space are much harsher. So the background temperature on average would be around minus 270 degrees Celsius. So extremely, extremely cold. So if we're talking about things that have extremely low energy. And so the ice in space, water in space, in nebula clouds, you've probably seen photos from the Hubble telescope, for instance, these sort of gas clouds, they'll be at very low temperatures and it won't have the energy effectively required to make these nice hexagonal symmetries. The atoms are moving extremely slowly when you're at that low temperature, and so they can't rearrange themselves into a nice structure. They're sort of trapped.
It's fun, isn't it, to think that ice needs some heat in order to be icy, in that respect, what we call ice. So why does that matter then, knowing whether it's in that amorphous state or in ice cube Earth state?
If you think of these amorphous solids, they're basically like a snapshot of the liquid. And so to physicists, it's a very, very interesting model for the liquid water. And now, to get a little bit technical, there's multiple different types of this amorphous ice that we know of. One of them is a low-density amorphous ice. Another one is a high-density amorphous ice. And so this idea basically risen to the theory that perhaps liquid water itself is a mixture of these two, a low-density liquid and a high-density liquid. And so this is one of the very interesting ways that amorphous ice feeds into the physics of how we understand something as important as liquid water.
And how have you been trying to probe this then? How have you been trying to get underneath whether that is the case?
In this theory, we want to understand really detailedly the structure of low-density amorphous ice. That was our aim, this most common form of ice in the universe. And it's surprisingly difficult to get a full atomic scale resolution, so you could literally see each atom, how it's arranged themselves in three-dimensional space, is really, really difficult to experiment still in this day and age. And so what we do in experiment was we have things called X-ray diffraction, a bit like how you go for an X-ray in the hospital to take images of materials. And we get back like a signal, just a line on a graph effectively. We don't have a full image of the ice. To complement this, where I come in is the computational physics side. So this is effectively where I would use computers to simulate water. So I basically put the laws of physics into the simulation and I can model water directly. It's a bit like how you'd put gravity into a video game, so your character sort of jumps up and down in a sensible way. I've generated a range of structures, things that were highly crystalline and things that were highly disordered, amorphous. And effectively, we were then trying to find what's the best match to what we see in experiment from the X-ray. It was kind of a Goldilocks situation, it was not too crystalline and not too amorphous. So what we found is actually we have this sort of happy medium around about 20% crystalline order. But basically the material, instead of being completely disordered, this low density amorphous ice, it's disordered, but has very, very tiny crystals embedded throughout it. So it's kind of like it's full of tiny diamonds throughout the liquid water.
The stuff that's out there in the bulk of the universe does still have some crystalline structure. But it's
Yes.
as you say, it's like a giant mess of small crystals rather than one giant crystal. Why does this matter? Why is this exciting to a physicist to know that that amorphous water out there contains an element of crystalline structure?
So I think there's three aspects. I think one is how it impacts our understanding for liquid water. And so, of course, understanding the nature of liquid water is incredibly important for a huge range of ways that we understand, life. A second would be, this is the most common form of water in space. And so there's a huge number of ways that this could impact cosmological phenomena. Quite an interesting one is this theory called panspermia, which is effectively that the building blocks of life landed on Earth via a comet. Bulk material of a comet is ice, and it is actually this amorphous ice. And so if this building blocks of life were to arrive via a comet, what we have there is organic material preserved inside the ice. The reason that doesn't work in reality is because crystals in solids actually damage our cells. A completely disordered solid would actually be a very good transporter for organic materials compared to normal ice as we know it. Our finding negatively impacts that a little bit because these crystals we'd have in the material mean effectively there would be a slightly worse carrier for organic material. And perhaps a third one would be, it's quite interesting. I think we've been studying this material for around about 90 years. And to find something like this where we actually change our understanding of the atomic structure, this is really, really important because amorphous structures are actually everywhere in our everyday life. If you think of fiber optic, how you get your broadband, a vital part of fiber optics is that it has no crystalline structure. It's completely disordered. And that's how we transport information across. Now, if there's a material like water where after 90 years of quite intensive studying, we can still change our atomic understanding of it, this raises the question this could be happening in an abundant different ways for technology as well. And so if we could remove the crystals, we could even improve technological materials for making fiber optic even better.
Michael Davis there. Well, to time now. And surprisingly, in July and August, time is going to zoom by ever so slightly faster. Earth usually takes 86,400 seconds to do a full spin, otherwise known as a day. But on the 9th of July, the 22nd of July and the 5th of August, our planet is expected to pick up the pace ever so slightly and trim a millisecond or so off the length of a day. Will we even notice? We'll hear from Ruth Ogden on that score in a minute. But first, what is actually up with the planet? David Gossard is a physicist at the University of Western Australia.
This is happening because of the orbit of the moon. Generally, the orbit of the moon slows the rotation of the Earth down over time, and this is a gravitational dance between the Earth and the moon and the Earth's tides. The moon pulls on the Earth's water and creates the tides, and that creates friction as the Earth rotates under those tides, and then there's this gravitational dance where rotational energy of the Earth is transferred into the orbit of the moon. So it means we're losing rotational energy and slowing down. Basically, if you wind the clock back 65 million years, the dinosaurs had a much shorter day than we do now. But the moon's orbit is not a perfect circle and it's not perfectly aligned with the Earth's equator. So it means the moon gets closer to the Earth and further from the Earth at different points in its orbit. And so that means the effect of the moon slowing us down is reduced. And with various other effects, so seasonal changes like where water moves or ice moves and builds up on the Earth's surface due to changes of seasons in the northern and southern hemisphere, we get a few days where we rotate very slightly faster than we normally do.
How on earth did this get picked up in the first place?
So we model these things, we can model them quite precisely. So the Earth-Moon interaction is relatively easy to model. Tides are very predictable, we can see those coming. The less predictable parts are what the Earth itself is doing. So things like as the Amazon River fills during its wet season or glaciers get more snow on them and get heavier, that shifts where water and ice and basically Earth's gravity is distributed across the Earth. So those things we can model to a certain extent, but there are some bits that are trickier to model, such as what the Earth's core is doing, so what magma flows are doing beneath our feet. But overall, we do generally have a good model of what these things are doing, and so we can predict in advance that we're going to get this speed up. So a 1.5 millisecond shorter day on a particular day. And when we actually come to measure it using stars as a reference, we may find it's close to 1.5 milliseconds, like 1.45 or 1.55.
Do you expect then that this is a blip effectively on those days for all the factors and all the reasons you've said, and that in the aftermath we'll get that millisecond back. We're not going to all be shortchanged a millisecond hereinafter.
Yeah, it's just these 3 days that are shorter than average. As I said earlier, the moon is slowing us down steadily. So over time, the Earth's rotation is continuing to slow. And so we will just get longer and longer days.
Does this make a practical difference? For us humans, I mean, it's neither here nor there, is it? I mean, some days it gets dark earlier because it's cloudier. But there are devices on Earth that are working to fractions of a second. I'm thinking to take money out from an ATM machine, you're using GPS data because the timing's got to be right. To trade money on the London or the New York Stock Exchange, we're using GPS signals and relativity to get the timing right. So when those sorts of times shift like that, does that have the potential to make differences?
Yes. So not this one event on its own, a single day or a few days being faster or slower by a millisecond isn't going to be noticed by anything other than the people making careful measurements of these things. What happens is, because we're slowing down and we accumulate more and more drift of this time, once we accumulate about 900 milliseconds, so 0.9 of a second, then we add or subtract a leap second. So it's a similar concept to a leap year. A year is actually 364 and a quarter days long. So to make sure our calendar doesn't drift out of synchronization with the sun over the course of a century or so, we have to add an extra day every 4 years to account for that quarter of a day. The leap second is a similar concept. Every time we gain about 0.9 of a second, we add on a leap second to our clocks, just to keep them in sync with what the heavens are doing.
Is there a master clock somewhere on Earth, David, to which all of the other clocks, like the satellite clocks and all the other examples you've been talking about, are all synced to? And if so, where is that?
There's a network of clocks. So various metrology institutes around the world, so NIST in America, the National Physical Laboratory in the UK, and various others around the world, all of them have state-of-the-art, very high-precision atomic clocks. And these get networked together to eventually calculate time reference. So there's no one master clock. It is all these clocks working together to create a master, which is UTC.
And hence, that's what would notice when we're a millisecond or so out. And it's
Yes.
against that we would make the correction.
Yes.
So in your work, sending huge amounts of telescope data over long distances, this is something you would worry about, but for the average Joe like me, I'm not going to notice.
Yes, as someone who works in sort of time and frequency measurement and astronomy, leap seconds are a very silly idea because at a human level, we don't care. These leap seconds are designed to keep our clocks aligned with the heavens. So we're keeping our very high precision, superior clocks aligned with this old archaic way of doing things that's far less precise. Why the heck are we doing that? As I said, we have daylight saving time. We have different time zones. We play with the time arbitrarily over a matter of hours as humans. These sorts of precision timing things only matter for our computer networks. So why do we bother adding leap seconds? It would take thousands of years before the leap seconds accumulate a noticeable human amount. So we should just do away with these leap seconds and let the sun and stars drift out of sync with our clocks for a few thousand years, because we're not going to notice. The only people who are going to notice are astronomers, and I think it's better that we update the pointing of the telescope to know, okay, the star's actually 1 second away from where we thought it would be, rather than getting our high precision clocks to update and our GPS systems to update, and potentially causing various glitches and problems. And so the international timing community have agreed that we're going to stop using leap seconds in 2035. And so I think that's a really good idea. I'm looking forward to that.
So make the most of your leap seconds. They're a dying breed. They'll be disappearing in under a decade. Thank you very much there to UWA's David Gozard for explaining why they happen in the first place. This seems, though, like a very good opportunity to think about how we humans respond to and register time, and the fact that most of us these days complain of being chronically short of it. Ruth Ogden is the Professor of the Psychology of Time, and she's at Liverpool John Moores University.
Time is really, really subjective. It's not like a clock would tell you. How you feel about a minute or a second is really heavily dependent on what you're doing and how you're feeling. So we construct time from our activities and our emotions. One of the issues that we face in modern life is that we just don't have enough time. We fill all of our time with a variety of activities, and this can mean that we don't really think about time in the way that we should. We see time as being a resource which should be spent, which should be used up, which can never be wasted. But really, for good well-being and good quality of life, we need to change how we think about time. So I completely agree with David. I mean, the odd millisecond here and there is going to make very little difference, if any difference at all, to the population. But what it does is raises our understanding and our awareness of time. It makes us appreciate that time is something that's important and something that we should take care of.
Where did we catch this kind of gotta be busy mindset from? Because I don't remember feeling like I do now when I was little, when I was growing up. And I don't remember my parents feeling that way, but they sure as hell do now, even in retirement.
Yeah, I mean, we live in a society where busyness and productivity is valued above almost everything else. So you have societal norms which are telling you to be busy, to always be active, to be constantly doing things. You have smartwatches which bleep you to tell you to stand up or to work more, or that you're stressed and you need to relax. So we've got this constant stream of pressure to not waste time. And as a result, we seem to have lost the art of doing nothing. We've unlearned how to relax and how to genuinely have unfilled time. As a result of that, what we often find ourselves doing is trying to relax whilst doing other things, so productive relaxation. So this might be looking on your smartphone and watching reels of cats or some other thing that you find some basic level of enjoyment in. But the problem we then have is that society tells us that this is a bad use of our time, that we should be promoting our intellectual growth or meeting with other people. So I think that the way in which we think about time has left us stuck between a rock and a hard place. We're supposed to be constantly busy, but when we need to relax, the things that we do aren't valued. And as a society and as individuals, we really need to think carefully about how we want to spend the time we have and how we can spend it in ways that make us feel good rather than fulfilling society's needs.
Is there any evidence, Ruth, that the life we are now living in that time-pressured mindset is translating into ill health?
There's plenty of evidence that time pressure is bad for all aspects of your health. Time pressure increases stress. It's associated with greater risk of heart attack. It's associated with risky decision making, poor mental well-being. It's even associated with greater levels of divorce. And there's some emergent evidence, coming back to what you were just saying about parenting, that time pressure and the impact of time pressure is intergenerational. So the children of time-pressured parents are themselves likely to feel negative effects as a result of the pressure that their parents are under. For me, this is the public health campaign that needs to be addressed. It's at the root cause of many mental and physical illnesses that are affecting society and individuals today.
Hard to imagine how we might start to chip away at it, though, isn't it? Because if you think about it, were I going to work 30 years ago, the rate at which I would work would correspond roughly to the rate at which my inbox would fill up, which would correspond to the rate at which the postman would bring the work for the day, or someone would arrive at my desk and drop some work off. Now, it's an all-you-can-eat email buffet of work coming in, distractions coming in, phones pinging, phones ringing. So we've kind of connected ourselves to an artery of incoming pressure that we didn't have before. But the workplace seems to exist and thrive on that. So it's very hard to see how we fix it.
This is a really good point, and we can look across to other European countries who are trying to address this through national legislation, such as the right to disconnect, which provides individuals with a legal right to not have to work or attend to their arteries of information beyond their working hours. But these are possibly ineffective because they don't challenge the social norm of busyness equals success. What we really need is for employers to have job descriptions and job roles which are the equivalent to one person's day's work. At the moment, we are in a situation where the role and the tasks within a job are vastly greater than the time that people have to fulfill them. And part of the issue here is that if we think back to industrial periods, jobs were based on time. So you would go to a factory between the hours of 9 to 5, and when you left the factory, your job was done. So it was a time-based model. Now we're much more fixed on a task-based model, and the number of tasks continually increases. And it's only when we reduce the number of tasks to be reasonable for one individual to do that we're going to be able to see this breakage in the model that we have now and an increase in free time.
Absolutely fascinating. Ruth Ogden at Liverpool John Moores University there. Well, now it's time for Question of the Week. And James Titko has been investigating a certain kind of bacterial infection thanks to this question sent in from Leonard.
I'd like to know about this Lyme disease and how it is acquired and the diagnosis. Thanks, Leonard. Lyme disease is caused by infection with a bacteria known as Borrelia. This parasite can travel through the bloodstream to many parts of our bodies, triggering immune responses and thus a range of symptoms, including skin rashes, fevers, potentially even neurological damage, and more. So how does it get into humans in the first place? Here's Jack Lambert, professor and consultant in infectious diseases at the Mater Misericordiae University Hospital at University College Dublin.
To the best of our understanding, you only acquire it from a tick bite. Certain ticks are carrying the Lyme bacteria, and when they bite you, they inoculate into your blood and you develop a bacterial infection called Borrelia burgdorferi, commonly known as Lyme disease. Some of the people get a rash around the site of the bite, and that's the classic bullseye rash. Once the bacteria enters through the skin, it gets into the bloodstream and it goes everywhere. So it can present weeks to months after the inoculum as joint pain, cardiac problems, tachycardias, brain problems, nerve problems. It kind of affects almost every tissue of the body. Even studies have shown up to a year after the original bite.
As many as 5% of ticks in the UK test positive for Borrelia, this remarkable, albeit pernicious bacterium, which has the ability to proliferate in ticks, mice, deer, our pets, and of course us. It makes humans sick by triggering an immune response and subsequently inflammation in many parts of the body. And it's the varied nature of these symptoms which complicate the next part of your question, Leonard, on diagnosis. But Jack believes there are other factors at play too.
The issue is that I think in the UK and Ireland, people are led to believe it's a rare disease, you know. In Ireland, they don't keep track of it, so they can make any numbers up. So say there's 100 cases a year. I think there's 2,500. The practitioners, it's not on their radar screen. That's number one. But the next challenge is the testing is imperfect. So I would say the standard tests that are used by the NHS in Ireland are about 50-50 accurate. So I have people say, oh, we did a Lyme test. You can't have Lyme. The test is negative. But the antibody test, in my opinion, is only about 50% sensitive. So you can have a tick bite, be sick as anything, and have a negative Lyme test. It's Lyme disease. You can have a positive Lyme antibody test from a bite you had 10 years ago. It can stay positive. It's your immunological memory, be perfectly healthy, and you don't have Lyme disease. Additionally, if you get the classic rash following a tick bite, that means the infection's already in your body, going into your bloodstream. You don't need to wait for an antibody test. You just treat right away.
So, Leonard, Lyme disease is acquired by tick bites, which transfer the Borrelia bacteria into our bloodstream. Challenges in diagnosing this disease include the many different symptoms, the imperfect testing, and perhaps a spot of bias in the medical community as to how common Lyme disease really is. If you have a bullseye rash, you should go to your doctor, who should start treating for Lyme disease straight away. Thanks to Jack Lambert, professor and consultant in infectious diseases at the Mater Misericordiae University Hospital, and to you, Leonard, for that question. Next time, we'll be answering this one from listener Laurie.
If we can put small nuclear reactors on submarines and Mars rovers, why can't those small nuclear reactors be used along with sustainables to power our towns and cities? Thank you.
Now, if you know the answer, why don't you drop into our forum? That's at nakedscientist.com/forum, and you can have your say there. You can also email me. It's chris@thenakedscientist.com, and do, of course, send in any questions, thoughts, or comments that you would like us to delve into on your behalf. Again, chris@thenakedscientist.com. On the fact that I don't yet know what's going to happen to me, I have no further updates for you quite yet, but I do expect to know something very, very soon. So watch this space. I promise to update everybody as soon as I know. You will know. And what I will say is thank you very much indeed to everybody who got in touch. A lot of you copied me into correspondence and so on. And I can reassure you and assure you, I read absolutely every single one of them. I was touched and extremely humbled by what you said, and extremely grateful as well. I did try to write back to as many people as possible, but it got to the point where I just couldn't keep up. So I am sorry if I haven't got back to everybody, but please rest assured, I guarantee I read 100% of what you wrote in, and I'm very, very grateful. That is where we have to leave it for this week, but do join us on Tuesday when very special anniversary. 25 years since the first draft of the Human Genome Project. I was actually in the audience when Sydney Brenner came to Cambridge and announced that tomorrow we're going to be seeing the announcement of the unveiling of the Human Genome Project, and that was a quarter of a century ago. What has happened since? I've been down to the Sanger Institute where a lot of the action happened to find out how it got going and what we've discovered in the meantime. The Naked Scientist comes to you from the University of Cambridge. We're also supported by Rolls-Royce. I'm Chris Smith. Thank you for listening. And until next time, goodbye.